So do you have any questions from the previous class? Yeah, good morning. So let us start. So in case of axisymmetric flow, so there is nothing new to learn. Whatever we have done, so that is in case of two-dimensional flow, that's exactly what we have done in case of axisymmetric flow. So that's why the statement is two-dimensional and axisymmetric flow. So axisymmetric flow, we mean that suppose if the streamlines are exactly symmetric about a specific line. So let us say this is one line. Now if the streamlines are, so that is like this. So this is called axisymmetric flow. So if it is a straightforward flow, then actually you may not find much of difference. But suppose if there is a cylinder present like this, and then this is the axis, and on this axis the streamlines actually will come like this and will go this way and this way. Now if you notice, for each line on the top, there will be a corresponding line at the bottom as well, right? These two together will form the system of axisymmetric flow. So this system is called axisymmetric flow. Got it? Understood what is an axisymmetric flow? Got it? So it is just an understanding of how the streamlines will be. So this is what we call as the axisymmetric flow. But there are nothing new to learn, because suppose if there are some sources and sinks that are present, now we will be deriving the streamlines equations the way we have done in the yesterday's case, right? Those streamlines, suppose if they are symmetric about a specific line, we say that it is an axisymmetric flow. Yesterday we have drawn, so that is, so this is x-axis and this is y-axis, and then there will be a circular streamline like this, and then from here, so this is how the flow is. Now if you notice, about the vertical line or about the horizontal line, the entire streamlines are symmetric, correct or not? If you take the horizontal line, the top lines and bottom lines are exactly the mirror image. Suppose if you take this as the vertical line, and then the right side part and the left side part is exactly the symmetric or mirror image about the y-axis. So these cases we call as the axisymmetric. Got it? So in case of two-dimensional axisymmetric flow, so the problems that are going to be asked are, so there are certain presence of the sources and sinks. For that you should be finding out the complex potential and the streamlines. And those streamlines, if it is symmetric, then we say it is an axisymmetric flow. If it is non-symmetric, we say simply two-dimensional flow. Clear? Got it or not? Any questions on this? Okay. Note down this. So axisymmetric flow, if the flow is, or if the streamlines are symmetric about a specific line, we call the flow is axisymmetric flow. Otherwise, it is called as two-dimensional flow. Two-dimensional flow. Got it? So fluid motion in case of coaxial cylinders. So this is one of the important concepts. So multiple times the questions were asked by UPSC in this particular case. So coaxial cylinder we mean, so there is one cylinder, let us say this is one cylinder. Now let us say there is one more cylinder like this. So these two are actually having the same axis of line. So that is exactly the vertical line is nothing but the axis of the cylinder. So this axis of cylinder is same for both the cylinders. This kind of system we call as the coaxial cylinder. Now if you look at from the top, the cross sectional area will be, this is how it will be. So this is system of coaxial cylinders. Now here, suppose if there is a cylinder that is present, maybe hollow cylinder or maybe it is completely filled with some metal, and this is one more cylinder. So these two cylinders are present in fluid. So if there is presence of these two cylinders with certain gap in between, obviously the fluid will be occupied in this particular region. Now actually this fluid is subjected to the motion of this cylinder and this cylinder. Now let us say both the cylinders started moving, then how the inside fluid will behave and what is the pressure that got accumulated on this inner cylinder and outer cylinder. So such kind of cases we should be analyzing this. Got it? Yeah. So now suppose if there is a presence of fluid in this region, now if there is a presence of fluid, let us say this is the vertical axis and this is the horizontal axis, this is x-axis and this is y-axis. Now both the cylinders started moving. So let us say the inner cylinder is moving with a velocity of u and the outer cylinder is started moving with a velocity of v, but exactly along y-axis. Now this is a most generic case. So this is moving in this direction and the outer cylinder is moving in the vertical direction. Now in general, if I take at certain angle, so the components of the velocities for both the things actually will be with certain angle like this. So this is the most general way of analyzing the coaxial cylinders, right? Now here this is moving along x-axis. Then in general the fluid at this particular location will be moving here and there like this. Got it? So the actual cylinder movement, there is a component along this direction, right? So this is a random component. So if you are able to find out the random component of velocity of the inner cylinder in this direction, then you will be able to find out in any direction by taking the corresponding component. Got it? Now here this is moving with the velocity of u and this is moving with the velocity of v, and let us say the radius of the inner cylinder is a and the radius of the outer cylinder is b. So this is b. Now to find out this particular case, we usually adopt one specific method. So that specific method is generic for all the kinds of flow problems. Not only flow, wherever there is a field involved, maybe electric field, maybe fluid field, right? Maybe gravitational field. In all such kind of cases, there is one specific method that is involved. That method is nothing but the solution of the Laplace equation. Laplace equation, del square phi equal to 0. So this is the Laplace equation. Now here, anyway, our fluid will satisfy the Laplace equation. Let us say, so Q is equal to minus del phi, and this is the velocity potential, where q is the velocity, and phi is the velocity potential. And then del dot q is equal to 0, which is nothing but the continuity equation. Is the continuity equation. For a possible liquid motion, continuity equation must be satisfied. Therefore, del dot q equal to 0. It implies del dot q is nothing but minus del phi equal to 0. It implies del square phi equal to 0. So this is what we call as the Laplace equation. So this is nothing but the Laplace equation. Now the beauty of this Laplace equation is, so if the Laplace equation is satisfied by any particular field, either it is a flow field or a fluid, so for an electric field or a gravitational field, so if the Laplace equation is satisfied, we have adopted certain methods to solve this Laplace equation. Any function which will satisfy this phi, del square phi equal to 0, is nothing but the solution of the the Laplace equation. Now this solution may be different in Cartesian coordinates, different in polar coordinates, in other coordinates it will be completely different, and then depending upon the scenario, you can involve a certain solution which will randomly satisfy this Laplace equation. Got it? So any function you can think of which will satisfy the Laplace equation here, the solution of that can be interpreted as the solution of this flow problem. Got it? So because this Laplace equation is derived from the flow equation. Here, now let us say phi is one solution, let us say AR plus B by R into cos theta. Just you note down this, I'll rewrite it, just note down this. So this Laplace equation in Cartesian coordinates, dou square phi by dou x square plus dou square phi by dou y square equal to 0. So this is the Laplace equation in Cartesian coordinates, but this is a cylinder. So this cylinder is nothing but polar coordinates on a plane. Now to adopt this case for Laplace equation, you have to identify the Laplace equation in terms of the polar coordinates or cylindrical coordinates. Now anyway you are treating at a constant z value, so this is nothing but the polar coordinate system for us. So in case of polar coordinates, the Laplace equation will be 1 by r times of dou by dou r of r into dou phi by dou r plus 1 by r square times of dou square phi by dou theta square equal to 0. So this is the Laplace equation in case of polar coordinates. Got it? You can note down this and remember this. Now one particular solution, let the solution of the Laplace transform, of the Laplace equation be phi equal to AR plus B by R times of cos theta plus CR plus D by R times of sin theta. Now this is a random solution. What I have selected here, it is a random solution which will satisfy this Laplace equation. Now actually from this you can bring this one, but it is very complex. But the thing is, if this function is satisfying this Laplace equation, this can be treated as one of the solution of the Laplace equation, which means that is nothing but one solution to this flow problem. And this A, B, C, D, so A, B, C, D values are determined based on the physical situation of that particular problem. Got it or not? So this is a general solution to the Laplace equation. This general solution, you can make it a specific solution to our problem by calculating this A, B, C, D values as per our requirement. Got it? Understood or not? So if you put this here, so this will satisfy. This is the solution of the Laplace equation. Is this understood, or do you have any questions on this? Because this is very much needed to understand. Because from now onwards we are going to use only this one, stating that this is the velocity potential directly. Clear? Okay. So now actually coming to our specific case of finding out the solution to this Laplace equation. So here the velocity, if I put it here, there is a horizontal component of velocity and there is a vertical component of velocity. This is u and this is v. Now if I take a random direction, let us say this is making an angle of theta, then the component of u along this particular direction will be u cos theta, and the component of v along the same direction will be v sin theta. Got it? U cos theta and v sin theta. So this is, let us say I call this as cylinder A and this is cylinder B. So this is the velocity component of cylinder B. Of B, and this is the velocity component. Let the outer cylinder is having radius B and moving with a velocity along y direction. Along y direction with a velocity v. Let the inner cylinder is having radius A and is moving along x-axis with a velocity u, then the component of velocity at an angle theta to the horizontal or to the x-axis for the cylinder A will be, so this is u cos theta, and for the cylinder B will be v sin theta. So understand this, u cos theta and v sin theta. So u cos theta, the component of this along this direction is nothing but the cos theta. Now v sin theta, that is the component of this along the same direction. Now the angle here it is 90 minus theta. So the angle is 90 minus theta. V cos of 90 minus theta is the component along this direction, which is nothing but v sin theta. Clear? Right? Now actually with this understanding, so in this particular scenario, we are intended to find out the value of phi and psi. So these are essential components for us to analyze any particular flow for us. So if you know the potential, you will be able to find out the velocity, pressure, or whatever is required. And if you know the streamlines, you will be able to find out the direction of flow, right? So these two are the essential components which we will be finding out with the help of a generic solution of Laplace equation. So that generic solution is, so AR plus B by R cos theta plus CR plus D by R times of sin theta. Now that is the generic solution. You have to identify the A, B, C, D values for this particular scenario. Clear? Note it down. So now here, so we know that, so velocity is nothing but minus dou phi by dou r, or this is minus del phi, right? So velocity is nothing but minus del phi. So horizontal component is minus dou phi by dou r, and this value is nothing but u cos theta. So this is minus dou phi by dou r, yet r is equal to a. So this is due to cylinder A. And similarly, vertical component. So this is outer cylinder, minus dou phi by dou r, at r is equal to b, this will be v sin theta, or dou phi by dou r at a is nothing but minus u cos theta, and dou phi by dou r at b is nothing but v minus v sin theta. Now we know that the solution of the Laplacian equation, this will be AR plus B by R into cos theta plus CR plus D by R into sin theta. Now dou phi by dou r, if you calculate it, this is A minus B by R square cos theta plus C minus D by R square sin theta. Now this is the solution of the Laplace equation. We have taken the derivative of it. So dou phi by dou r at r is equal to a, that is minus u cos theta. Dou phi by dou r at r is equal to b, that is minus v sin theta, right? Now if you try to equate correspondingly, that is dou phi by dou r at r is equal to a, this is a minus b by r square, so you can replace a square into cos theta plus c minus d by a square into sin theta, and this is equal to correspondingly minus u cos theta, minus u cos theta. That means a minus b by a square is equal to minus u, a minus b by a square is equal to minus u, and c minus d by a square equal to 0. So this is two equations which involves four constants a, b, c, d, right? This is one set. Similarly, if you put r is equal to b, that is dou phi by dou r at r equal to b, so this will be a minus b by b square times cos theta plus c minus d by b square times sin theta, and this value should be equal to, so minus of v sin theta, right? Now equate the corresponding terms. So sin theta, c minus d by b square is equal to minus v, and a minus b by b square is equal to 0. Now this is another set of equations. So we have got four different unknowns and four different equations. All together we can solve for the values of a, b, c, d. Now if you back substitute these values in the original Laplace equation here, that is nothing but the solution of the Laplace equation, which is nothing but the velocity potential of this particular scenario of the fluid. Got it? Understood or not? So this is, the concept is straightforward and simple. So only thing is you need to understand or at least to study once, so that you will be able to solve any kind of problems that are related to this. So note down this. General equation, that itself is a separate study, right? So as I told you, Laplace equation is a powerful equation. So that Laplace equation has solutions for multiple problems in multiple domains of mathematics. Now here, so there are certain research that was done on Laplace equation itself to find out the solutions. There are many solutions, almost infinite number of solutions are available for Laplace equation. In that, we have selected one. Now if you want to find out the solution of the Laplace equation itself, use partial differential equations and then try to find out your own solution for it. Got it? Now, based on the solutions of these four equations, so A is equal to UA square by B square minus A square, and B is equal to UA square B square divided by B square minus A square. UA square B square divided by B square minus A square, and C equal to minus VA square divided by B square minus A square, and D equal to minus VA square B square divided by B square minus A square. So these are the four different constants which you are going to get it as a solution for it. Now, if you want to find out the velocity potential, is nothing but AR. So A is UA square. UA square or actually in general you can take out A square by B square minus A square. If you take it out, then U times of, so U A square divided by B square minus A square, you can take it out, then what is left over is R plus B square by R into cos theta plus, so minus V A square by B square minus A square. If you take it out, then here what you are left with is R plus B square by R times of sin theta. So this is nothing but the velocity potential. Clear? So this is A square. Yeah. Yeah. So VB square, if you take it out, what is left over here? It is I think this is B square. Yeah. Now it should be correct. Yeah. Got it? Now from this actually you can find out the streamlines equation. That streamlines equation with the help of CR equations, what says is dou phi by dou r is equal to 1 by r times of dou phi by dou theta. So this is the CR equations. Now take the derivative of it and then try to equate to 1 by r times of dou psi by dou theta. Dou psi by dou theta, then integrate with respect to theta, then you are going to get the streamlines equation. So once you got the solution for the Laplace equation, we were able to identify the solution that is nothing but phi, which is nothing but the velocity potential for us. From the same velocity potential equation, with the help of CR equations, you will be able to find out the psi value as you know the phi value. Got it? So dou phi by dou r you know. So you have to find out 1 by r times of dou psi by dou theta. You can equate it here, and then dou psi by dou theta r you can take it out and integrate it. You will get the psi value. Got it? You note down this. We are going to do that. So the value of c, is it not vb minus vb square by b square minus a square? Rishi? So what is the value you have calculated? So instead of b square, it is a square. So if you solve this, actually you are getting a square, right? So can somebody else confirm this? So this equation is correct, right? Okay, so let me cross check it. So what we have got is phi is equal to AR u a square by b square minus a square times of r plus b u a square b square divided by b square minus a square into r square. AR plus b by r, yeah, plus CR, that is minus v. So we take with a square first, v minus v a square, b square minus a square times of r plus minus v a square b square divided by b square minus a square into r. And here it is cos theta and here it is sin theta. Now this part anyway we don't have any issue, that is u a square by b square minus a square. If you take it out, then what is left over is r plus b square by r times cos theta, and then from here if you take out minus v a square by b square minus a square, yeah, I think so, you are correct, r plus b square by r into sin theta. So if you take out b square from here, then you are not getting, right? Yeah, I think it should be b square only. So as per the textbook, it is b square only. Maybe we have to solve this and then verify this. So in the textbook, actually he made the reference. So this was given as a square, but finally the answer is this way. That means he has treated this as b square rather than a square. So I thought it is a typo mistake. Anyway, so we can solve this and then identify, and then the final equation what we are going to use it is this one. Yeah, this one. Got it? Anyway, so I will also cross check it. So the solution of this should be exactly equal to what is the complex potential we have treated. That is the most general solution. Phi is equal to u a square by b square minus a square times of r plus b square by r minus v b square by b square minus a square times r plus a square by r. So this is the complex potential. Got it? Yeah. So this complex potential, with the help of CR equations, dou phi by dou r is equal to 1 by r times of dou psi by dou theta. Now dou phi by dou r, if you calculate for this, dou phi by dou r is equal to v u a square by b square minus a square, and then 1 minus b square by r square minus v b square by b square minus a square 1 minus a square by r square, and this should be equal to 1 by r times of dou psi by dou theta. So if you take r onto the other side, so dou psi by dou theta is equal to u a square by b square minus a square, then r minus b square by r minus v b square by b square minus a square r minus a square by r. Now this dou theta, so psi is equal to integral of u a square by b square minus a square into r minus b square by r cos theta. I think I forgot cos theta. So this is sin theta, and this is sin theta, and this is cos theta. Cos theta minus v b square by b square minus a square into r minus a square by r into sin theta. Now for this, actually you need to integrate with dou theta. Got it? So that will be the final solution, is nothing but psi is equal to u a square by b square minus a square into r minus b square by r, derivative of, so integral cos theta is sin theta minus v b square by b square minus a square r minus a square by r into, so integral sin theta is minus cos theta, so this will become plus. Got it? So this is a streamlines equation. So psi is equal to constant will give the streamlines for us. This is what we call as the stream function. Got it? So both we have got the phi value and we have got the psi value. So indirectly we got the complex potential. Clear? So this is how you will be finding out in case of motion of two different cylinders which are moving perpendicular to each other. So the fluid is getting distributed in such a manner. So the equation of the potential will be represented by phi and the streamlines equation will be psi. So this is the stream function. So for a constant value of stream value, this is a streamline it is going to represent, right? So how this fluid is moving, the equation of that will be this. Clear? At any instant of theta, you can find out the direction of the fluid there. So this is the greatness about the Laplace equation. So for any such kind of cases, we will be able to analyze without even knowing the fundamental principles behind it. So you just need the Laplace equation, nothing more than that. So if you have the Laplace equation, the solution of that will be represented based on the initial condition. You will be identifying the direct solution for that particular scenario. So only thing is you need to identify the constants based on the initial conditions. Clear? Any questions on this? Got it? So with this, I would like to stop the class for today. So tomorrow, actually, based on this concept, I am going to solve two different problems. Both were asked in the previous years. Got it? So the concept is straightforward and simple. Nothing new we are doing. Only whatever we have done now, right? So the same thing we will be doing in both the cases. Only thing is actually he will be asked us to find out the pressure. So for that actually we will be using some extra conditions. That extra conditions are, one is the pressure at any point is given by rho times of the scalar potential. This will give the pressure. So this is the relation between the pressure and the scalar potential. This is one relation what we are going to use it. And another relation what we are going to use, the pressure related to the velocity, because till now whatever we dealt with is nothing but only with related to the velocity, right? Now, what is the relation between velocity and pressure? That will be given by the Bernoulli's equation. So, Bernoulli's equation, what it says is, so P by rho plus half rho Q square plus the potential energy is equal to constant. This is Bernoulli's energy, Bernoulli's equation. Now, most of the cases, whatever the problems we are going to deal with, the potential energy is constant because at the same height we will be dealing. So, usually we treat this as P by rho plus half rho Q square is equal to constant. Based on this, we will be relating the velocity with respect to the pressure. Got it? So, the questions that are going to be asked is to find out the pressure. That is the kind of question he is going to ask. Now, for that, the relation what we are going to use is, one is the pressure with the help of the scalar potential, you will be able to find out this pressure. Now, this pressure, if you wanted to relate with the velocity, then P is nothing but rho Q square. So, P by rho plus half rho Q square is nothing but the constant. So, this is what is the Bernoulli's equation, what we have learned. So, this I have derived already. Got it? So, based on this understanding, tomorrow I am going to solve it. 2 problems. Got it? Yeah. So, thank you.